We now understand pretty well how to tell which part of the sky is going to be visible at any given time at any given location on Earth. We have a missing ingredient, which is this mysterious sidereal time. We need to understand sidereal time. Associated to this is another small omission. We've discussed the position of all the stars on the celestial sphere, but we've forgotten one star, one that might have some impact on our lives here, namely our local star, the Sun. The Sun, like everything else that is not on Earth, is somewhere on the celestial sphere in the sense that it rises in the east and sets in the west as the Earth spins or as the celestial sphere spins. And so we can locate the Sun somewhere on the celestial sphere, but I haven't told you where. And where that is somewhat interesting, because if you put the Sun somewhere on the celestial sphere, there's a whole section of sidereal time, a whole period of the 24-hour rotation of the Earth, when the sidereal time is close to the right ascension of the Sun, when the stars overhead include the Sun, and we do not do astronomical observations, at least not in visible wavelengths. And so it's somewhat important to figure out where the Sun is, and this will turn out to be at the root of this sidereal time issue. And so let's see how that works. This simulation might help us to explain what's going on. We know that in addition to spinning around its axis daily, the Earth also orbits the Sun once a year. Equivalently, if you prefer a stationary Earth, the Sun orbits the Earth once a year, from the point of view of who sees what when. The two are completely equivalent. The Earth orbits the Sun in the same sense in which it spins about its axis, and what that means is that as we see it, the Sun also orbits us in the same sense in which the Earth spins about its axis. In other words, the Sun appears to orbit Earth once a year, moving from west to east along the celestial sphere. What that tells us is that the Sun cannot be assigned a fixed right ascension. Its right ascension changes over the year. As the Earth orbits, if we start at some point on the Earth's orbit with the Sun in this direction in the sky, imagine the celestial sphere outside this figure, at celestial midnight, then 3 months later, when the Earth has moved to this point in its orbit, the Sun has changed orientation relative to the Earth. The Sun's right ascension is now 6 hours, and furthermore, 3 months later, the Sun's right ascension is 12, and 3 months further on, it is 18 hours, and after a complete rotation, the Sun will have made a complete circuit of the celestial sphere, moving to the east in the direction of increasing right ascension, so that the Sun's right ascension goes through a full 24 hours in the course of a year. You can't assign the Sun a fixed position on the celestial sphere. Rather, it moves along the celestial sphere to the east at the rate of one rotation per year. Now note, the celestial sphere is moving from east to west as it rotates around the Earth. The Sun is moving along the celestial sphere from west to east. This is important, so let's think about it again. As the Earth spins about its axis once a day, it also orbits the Sun once a year, moving in the same direction, which means, as seen from Earth, the Sun orbits us once a year, so that means the Sun moves along the celestial sphere, moving from west to east, in the direction of increasing right ascension to the east, and it completes one revolution per year around the celestial sphere. This means that which stars are invisible because they're only up at the same time as the Sun, well, that changes over the course of a year, so all stars get their chance to shine, so to speak. That is good, we get to see the entire sky. It also means that since the Sun is moving across the sky from west to east, while the celestial sphere is rotating from east to west, the Sun is carried by the celestial sphere, so it rises in the east and sets in the west. But its motion across the sky is a little bit slower than the motion of the stars. How much slower? Over the course of a year, the Sun moves backwards along the celestial sphere by one complete revolution. Let's see that extra day one more time. This simulation will help us to understand the consequences of the fact that as the Earth spins, it's also orbiting the Sun, and therefore the Sun is moving along the celestial sphere. To make things a little more clear, we have pretended that the sidereal day, or a day, is not 24 but 240 hours long. This will make the effect much clearer. So imagine that we begin our simulation with the Sun directly overhead for this tallest observer on the Earth. So this observer will presumably think that it is noon, and now let a sidereal day go by. The Earth will have completed a 360-degree rotation. Note it's oriented in exactly the same way it was before. However, it is not yet noon. The time it takes from noon back to noon again is longer than a sidereal day, because in the course of this rotation, exaggerated by a factor of 10, the Earth has moved along its orbit. There's this extra bit of rotation required to get to noon. From the point of view of Earth, this is a consequence of the fact that over the course of the day, as Earth spun about its axis but also moved, the sun moved in this direction to the east along the celestial sphere. We can do that again. 360 degrees rotation and a little bit required to realign us to the sun. Indeed, the time from noon to noon is longer than the time it takes Earth to rotate by 360 degrees by about 1 over 365 of a day, because the sun moves back along the celestial sphere by 1 over 365 of its complete annual rotation of the celestial sphere. That's about 4 minutes. So which of these is 24 hours, do you think? Is an hour going to be a 24th of the time it takes the Earth to rotate 360 degrees? Or would you define an hour to be a 24th of the time from noon to noon? Clearly you want it to be the time from noon to noon. Our clocks keep solar time. The reason for this is because, as we saw, while the difference between a sidereal day, 24 hours, and the time from noon to noon is only 4 minutes, these 4 minutes accumulate over the course of a year to a complete day. If you tried to work with a sidereal clock, then if you started it out such that noon fell at 12 hours sidereal, 6 months later, noon, the sun overhead, would fall at 0 hours sidereal, and if you tried to operate by the sidereal clock, you would want to have lunch when it was darkest. This does not work very well for agriculture, though it is very good for astronomy, because sidereal time keeps track of the stars. The clocks that run our life, of course, keep not sidereal, but solar time. We call that local time. And so what that means is that these solar clocks, or local clocks that keep solar time, run slower than a sidereal clock. 24 sidereal hours, 1 360-degree rotation of the Earth, is less than 24 solar hours, the time kept by our clocks, by about 4 minutes, a little less than 4 minutes, 1 over 365 of a day, to be precise. So our sidereal clocks run faster than the clocks that are used to measure time. So how do you relate the two? Well, we have this issue of two clocks, one of which runs faster than the other. They're both 24-hour clocks, and so at some point they agree, and then the faster clock runs ahead, and it will remain ahead until it has completed one full 24-hour rotation more than the other clock, and this takes, by definition, precisely a year. So once a year, there is a day when sidereal and solar clocks agree, and by convention, that day is set to happen, we'll see why in our next lesson, on or about September 21st. So on or about September 21st, wherever you are on Earth, your sidereal time is approximately equal to your local time. Now, I should qualify this. Remember, local time varies from position to position continuously. Local time also varies from position to position. If you move about 15 degrees east in longitude, then local time is an hour later. That's what time zones are about. But for the convenience of arranging train schedules, we don't let local time vary continuously so that each town has its own local time. Local time is fixed over an entire 15-degree slice of the Earth and then jumps by an hour, whereas sidereal time is defined locally, so varies continuously. So even when I say sidereal time equals to local time, I mean to within half an hour, which at the precision that we're working is good enough. So on September 21st, to within this half an hour in precision, sidereal time is equal to local time. And then if we know that, we can compare the two at any time before or after September 21st, because we know that the sidereal clock runs faster. A solar day is 4 minutes longer than a sidereal day. So a day later, the sidereal clock will have run ahead and be 4 minutes fast, and D days after September 21st, the sidereal clock is ahead of the local clock by D times 4 minutes. D days before September 21st, it was behind by 4 minutes and catching up. Now, of course, this is approximate. 4 minutes is not precise. We are in any event ignoring time zones. Beware of daylight savings time. This expression, of course, ignores the jump by an hour that we artificially introduce into our clock. So this is standard time. But if you want to, this is good for dates that are near September 21st. We can rescale this at the 4 points of the compass, if you will, of Earth's orbit. So on December, respectively March, respectively June 21st, you can reset things. So sidereal time is local time plus 6, 12, 18 hours. And then on September 21st, the difference will become 24 hours, which is the same as 0. So now we know how to find sidereal time. And now that we know how to find sidereal time, let's use this to solve an actual problem that might interest us. So suppose that we are interested in looking at the bright star Vega in the constellation Lyra, and we want to know when Vega might be visible in the sky as high as it can around midnight. Now, Vega, if we look it up, has a right ascension of 18 hours and 36 minutes. According to what we said, Vega is at highest in the sky. It is crossing our meridian when our local sidereal time is 18 hours and 36 minutes, when our local meridian corresponds with the meridian on which Vega lies. I want to know, when is this going to happen at midnight? Well, this will happen when local time of 24 hours, which is the same as 0 hours, corresponds with sidereal time equals 86 hours and 36 minutes. Well, if you look back at the previous slide, you'll realize that on June 21st, we had sidereal time was approximately local time plus 18 hours. And so if we wait 9 days later, sidereal time will be local time plus 18 hours plus 4 minutes times d. If we want 4 minutes times d to be 36 minutes, d is going to be 9 days. And Vega will be high overhead at midnight, 9 days after June 21st, on or about June 30th. This might explain to you why the group of stars, the bright triangle of bright stars that included Vega, was something I called the summer triangle. And so now we finally have a way of understanding what the sidereal time is, predicting which stars will be overhead in which season, and at any given time, we can map what the picture of the sky is that we'll see. So we have a complete solution of the mathematics problem we set out to solve, describing which part of the sky will be visible where and when. Congratulations!